Thank you for this introduction, and thanks a lot to the organizers of this program for their invitation. And it's quite a challenge to be the first speaker of this nice program, but I try to overcome the challenge. So, as said by Vivek, I will speak about the intertwining, the Markovian dance between Monte Carlo sampling, and optimization. And so they are intertwined. So the intertwine why? So first, let us consider the first point of view. We are interested in sampling, and we will have to use some optimization tricks. Why? Why? Because, for example, assume that we want to sample from a target distribution pi. And if you use a classical, naive, crude Monte Carlo sampler, it may happen that depending on some characteristic of the target density, for example, the multimodality of the density, it may be naive. Classical samplers may have a very poor behavior. But they also depend on some design parameters. For example, if you are familiar with the Hastings-Metropolis algorithm, in the Hastings-Metropolis algorithm, with a symmetric random walk proposal, let us say with a Gaussian proposal, what you do to sample points is, starting from a current point, you then propose a Gaussian distribution centered at that point with some covariance structure, and you choose, as a user, you choose the covariance structure, and then you propose this point and you accept or not this point with a rule which depends also, of course, on the target distribution you want to sample from. And the choice of this covariance structure of the proposal mechanism has a great influence, a very large influence on the efficiency of the sampler. So there are many studies in the literature that tell you that the optimal choice in that case is to choose what I will call the design parameters, theta. So here theta in my example is a covariance matrix, is to choose this covariance matrix as a constant, which is explicitly known, a constant multiplied by the covariance of the target distribution of pi. Usually in real life, you don't know the covariance of pi. If you are not able to sample exactly from pi, it may be also difficult to know the covariance structure of pi. And so we try to learn by using samples of from Hastings-Metropolis, for example, algorithm. You will try to learn this covariance structure. So at the same time, you sample and you try to learn a quantity which is characterized as the root of some criterion or as the argmin of some criterion. But unfortunately, the function or the criterion is usually intractable. So you have two strategies, hopefully. The first one is, first, as a preliminary machinery, you introduce a preliminary machinery in order to solve this, approximately solve this criterion. Then you obtain an estimation of the optimal value of the design parameter, and you plug this estimation in your sampling mechanism. It's not efficient at all because you have this first machinery which uses samples, and then you forget everything only to keep in mind the estimation of the design parameter, theta star. And so you would like to learn and sample at the same time, and in that case, it is a strategy number 2, which we'll explore. We will explore it this afternoon. No, yes. Now you are on the other point of view. You are not especially interested in sampling, but you are interested in solving an optimization problem. It may happen that this optimization problem is expressed in such a way that the objective function, you want to find the root or you want to minimize, the objective function is not explicit. But, and this is the reason I'm interested in these cases, but this objective function is defined as an expectation which unfortunately, is intractable, and in many cases, you are not able to exactly sample from the target, the distribution, which is natural when writing this criterion. So typically, it may be the first situation. There are also other problems in optimization that may come from the fact that the objective function is not available, but it doesn't matter. Typically, if you use a gradient technique, the fact that the objective function is not known is not really important. You are more interested in computing the gradient of the objective. But it may also happen that this, what I will call auxiliary quantities, are not available anymore, no more. Which means that typically the gradient is not available, or if you use other strategies, which are also popular in statistics, if you use other strategies, you can try at each iteration of the optimization solver, you can try to find what we call a majorized minimization method, which means that you have your objective function, you will find a function that majorizes this function, and you will minimize this majorizing function as to define the new value of the parameter. And here again, in some cases, the computation of this auxiliary function is not possible exactly. So the strategy we will explore in this lesson is a strategy when, since the objective function or auxiliary quantities like the gradient or like these auxiliary functions are expressed as integrals, the idea is to approximate these integrals by using Monte Carlo techniques. Which means that if there exists in the literature result addressing the convergence of optimization techniques when you are able to exactly compute all this quantity or the quantity which are required, for example, the gradient. The problem is now if you introduce an error at each iteration of the algorithm, because you replace the gradient by an estimation, what happens with this perturbed algorithm? Will it inherit the same asymptotic behavior as the exact one? What about the convergence rate? What about many implementation quantities which are required? For example, if you approximate the integral by a Monte Carlo sum, how many points in the Monte Carlo sum? And many questions like that you have to address in order to be sure that your perturbed algorithm will behave like the exact one, which is what you would like to reach. So in my talk, in these lessons, what I will insist a lot, and which will be maybe for some points the novelty of the results, I will insist a lot on the Markovian framework, which means if you are interested in sampling, but you have to use in the background an optimization process that tells you how to feed your sampling mechanism, I will consider sampling mechanism based on a Markovian transition. Now, if we are interested in optimizing, I will consider techniques where when the quantities that have to be approximated in order to implement the optimization algorithm, the quantities rely on points sampled from a Markov chain. A Markov chain, or let us say a chain, because I will consider the more difficult situation when each point is sampled from a Markov kernel, starting from the previous value, but you see that this Markov kernel is indexed by the current knowledge of the quantity. Typically in the Hastings Metropolis sampler, if you try to learn the covariance structure, the perfect covariance structure, at iteration t, you have a current estimate of this covariance matrix. You use this current estimate to produce a new point, and then with this new point, you update the estimate of the matrix. And so for the next iteration, you will use another estimate, an updated estimate of the covariance matrix, which means that in practice, you have a family of Markov kernels. They are all indexed by some quantities denoted by theta. This theta is random in our process. It is defined in the background. It evolves. And at each iteration, we use the current value of theta to update the next point. So I will call this kind of chain controlled Markov chain. This morning, I will introduce essentially two motivating examples. A motivating example from the optimization, the simulation point of view, and then the second one from the optimization point of view. Both of them are motivated by computational statistics because it's my domain of interest. I do Markov chain, I do MCMC, and I work on stochastic algorithm design or used to solve statistics questions and estimation, mainly estimation in statistics. And then this afternoon, I will discuss on the convergence, sufficient conditions for the convergence of controlled Markov chain. Tomorrow morning, I will discuss on sufficient conditions for convergence of stability, essentially, more than convergence of stochastic approximation scheme when fed with these controlled Markovian samples. And my talk, the talk tomorrow afternoon, will use all these things to present the recent results on perturbed proximal gradient algorithm. So today, motivating example. A first example in 6 slides, which is an example from the family of the adaptive importance sampling algorithm, and more precisely in the family of what we call the Wang-Landau approaches. So this algorithm were designed in order to address the following problem. We have a target density, pi, which is highly multimodal. So here it's, for example, I draw such a density on R2 with different point of view. Here are the level set, and it is highly multimodal, which means that if your algorithm starts, for example, in this area, it is not able to jump easily on the other side, which means that you are interested, if you use classical algorithm, it will not be able to do that. And so you want to design algorithm which in such a way that the chain is able to explore all the domain of interest of the target distribution pi. So here, for example, I show you the behavior of 2 different algorithms. I show you what I display here is as a function of the number of iterations. I show you the x path of the chain. So it starts in the negative part, which means it starts in this, no, negative is there on my plot, it doesn't matter. So it starts here. It stays a long time in the negative part, and then we don't know why he's able to jump on the other side. And so he moves in the positive x-axis, and then he stays a long time here, and then able to go back on the side, and so on. Here, it is another mechanism to approximate pi, and you see that this algorithm mixes as better mixing properties. He's able to move. I only show you the x path, but because the difficulty is in this direction, but he's able to move far more easily between the left and the right. And just the scale of time here corresponds to this one. Just to show you that this one, I think, is a classical Hastings Metropolis algorithm, maybe an adaptive one where we try to learn the covariance matrix, but when the algorithm only sees it, when the algorithm only sees this part of the target density, he learns a very bad covariance matrix, so it takes time to jump to the other one. And this path is obtained by the Wang-Landau approach. I will now detail. So the Wang-Landau is among the family of the adaptive of the importance sampler, which means that we have to find a nice proposal distribution in order to sample under this proposal distribution, then compute an importance ratio, which is in order to correct the fact that we did not sample under the exact target distribution in order to approximate pi. And in the Wang-Landau approach, you decide to consider a proposal mechanism, not only one. You have a priori many proposal mechanisms available, which are all defined as follows. So as a user, first, you have to define strata. It's fixed for all the algorithm. So you choose the number of strata, which means a partition of the state space. Let us say that the state space is RD. And denoted by x1 until xi. And what you do is that you decide to define the proposal mechanism as a local on each stratum. You reweight the density pi by a scale factor theta I. And here it's a normalizing constant. Theta star is a normalizing constant, which means that theta star is defined as the mass of the stratum number I under the target distribution pi. So you have this local reweighting. And the optimal, which is known to be optimal, is to choose this local reweighting, to choose theta as what I will call theta star, which collect all the weight of the strata, of the I strata. And it is optimal for the following reason. If you compute pi index, the mass of the stratum number I under the distribution indexed by this theta star, what you will obtain is that you will obtain the normalizing constant, theta equals theta star. So here you have 1 over, yes, you have I, and here you have some, you have, let us say K, which means that you have exactly 1 over I. So it means that if you choose this value of the weight, your proposal mechanism will give the same mass to each stratum. It is a uniform distribution on each stratum. So for example, in the previous example, since the difficulty is to move on the x-axis, you can choose the strata as lines, as partitioning the x-axis, and your proposal mechanism will spend the same time in all the strata. So you will force the proposal mechanism to be able to visit the deep valley, and so you will be able to move from one mode to the other one. What is the problem? There are two problems. The first one, I will comment a lot, is the fact that this optimal value, theta star, is unknown. Theta star is defined. Remember that each component of theta star is the mass of the stratum number I under the target distribution. And in the real-life application, this quantity is unknown. For physicists, it is related to the free energy, up to a log. So it is unknown. It is not available, so you have to learn it. And the second problem, but I will not comment it today, but the second problem is that if your proposal mechanism spends the same time in all the strata, it means that it will propose many points which are not interesting on the point of view of pi, and so you have to find a clever way to reweight the points you obtain. So I will not comment this point today because, and this week, because I did not decide to have a full to give details a lot on Wang-Landau techniques, but there exists in the literature more advanced algorithms that I will, than the one I will comment today, that address this problem of inefficiency of this proposal distribution. So keep in mind that we would like to be able to sample under pi index by theta star, but theta star is not available. So if pi theta star were available, what we would do, the algorithm would be the following. We sample point under this target distribution, or if we are not able to sample exactly under pi theta star, we could replace exact sample by MCMC sampler targeting pi index by theta star. And then, once you have this point, you compute the importance ratio. And here, if you compare the expression of pi and the expression of the proposal mechanism, the importance ratio is given up to the number of strata, is given by the coefficient theta star. If the point xt is in the stratum number I, then the ratio is constant and is equal to theta star of I. So if theta star is known, you are able to sample from the perfect proposal mechanism, and you also have the knowledge of the importance ratio value for each point. And so typically after that, if you want to approximate integral with respect to pi, you compute the mean value, so with t, capital T samples, you compute the mean value of the function evaluated at this point, multiplied here by the importance ratio. Since you don't know theta star, you have to learn it. So theta star is defined as the mass of the stratum number I under the target distribution. If I know theta star, sorry? Yeah? Here? What happens is that it makes far better than the classical one. If you know theta star, you can exactly apply these techniques, for example. And here you are able to compute exactly the importance ratio. And if you are also able to sample exactly from pi theta star, you can prove that this importance, that this estimator converges to, yes, we have proven proof even in the case where we sample from a MCMC sampler. We have proved convergence, almost sure convergence, convergence in expectation, convergence in this, and we also have a CLT, I think, on this kind of. So theta star is unknown. So theta star is unknown and is defined as an expectation of the indicator of the stratum number I, and it can be seen also, it can be characterized as the unique root of a function, a mean field, a function here, which is defined, so theta is a vector of size, the number of strata, and each component, h indexed by I, each component is given by this formula. I explain you roughly the intuition of this formula. So, the intuition is the following. If sampling from pi were available, if we were able to sample exactly from pi, in order to estimate this quantity here, what we could do is we could define a counter saying that at time number t plus 1, it is the counter as the previous one, plus we can introduce a leverage effect multiplied by 1 if the current sample is in the stratum number I. You increase the counter by gamma every time you have a point in the stratum number I. This is a counter, it's not a weight, so associated to this counter, you can define the normalized one, which is the sum over all the counter of this. Pi is not available, but now if you have sampling from pi theta, if we are, in that case, you could do exactly the same, but here you have to introduce the importance ratio in order to correct the fact that you do not sample from pi, but to sample from pi theta. And the importance ratio is equal or is proportional to theta I, which means that you modify the formula like that. But you would like exactly to sample from pi theta star, which is unknown. And so what you can do is to replace. What you can do is, if you don't have at time t an estimate theta t of theta star is known. And so what you can do is to replace this quantity by its current estimate. So at the end, what you have, your update formula of the counter is the new counter is the previous one plus a leverage effect multiplied by the current estimate of the importance ratio multiplied by 1 or 0, depending on where is the current sample. Then you normalize. You normalize, saying that it is this quantity plus gamma theta ti, the indicator, divided by the sum of so I put this in factor, 1 plus gamma divided by the sum theta t I'm lost. Okay, here it is J, the indicator. Should be like that. And here you have this quantity here, which is nothing more than theta t of I. And here you will put this quantity like that, so you obtain theta t of I plus gamma divided by the sum multiplied by theta t I indicator and this quantity divided by 1 plus something, you do an approximation at the first order of 1 over 1 plus something, like 1 minus, and you have these things. So it is like that. It should give you, I forget something. Yes, I forget. The theta I should be outside. So this update rule here can be understood as a first order approximation, first order with respect to this quantity of this mechanism of counting the number of visits to the stratum number I. So here there are different strategies, which means that in the literature there are different Wang-Landau algorithms depending on this updating scheme here. So it can be shown, and I don't detail here, but it can be shown that the unique root of this associated to the mean field, that is the integration of this, is given by theta star. And so if we want to estimate a way to estimate theta star is to run a stochastic approximation algorithm. We tell you that the new estimate of theta star at time t+1 is the previous one plus gamma multiplied by this quantity, evaluated at theta equals theta t, and x equals the current sample xt+1. xt+1 is sampled under the current, not pi indexed by theta star, but the current estimate of theta star, pi indexed by theta t. And if you are not able to exactly sample from this target distribution, which is what happens usually, you can replace this exact sample by a MCMC sampler having this target distribution as invariant distribution. Yes? There is a theta I would like to reach, theta star. So I will run a mechanism to learn it, and this mechanism will govern the way I sample the point. Yes, theta star is defined at the beginning as is defined here. It's characterized by the problem, by the target distribution. It's fixed, but it is unknown. Yes, it's fixed and unknown, and you want to learn it. And what I try to discuss here is to show that a way to learn it is to run a stochastic approximation with this mechanism. With this function h, I try to justify the expression of the function h, and then fed with not ID point from pi theta star, because theta star is unknown and ID points is quite unlikely. So we replace pi theta star by pi indexed by the current estimate, theta t, and even ID point is replaced by one-step MCMC. So now that the algorithm now is the following, is that we sample a point under MCMC sampler having pi indexed by theta t as its target distribution. And then we use this point to feed a stochastic approximation scheme that will learn the value theta star. What is the intuition? It is expected that the sequence theta t will converge to theta star, which means, roughly speaking, but we have to prove it in a rigorous way, that the invariant distribution pi indexed by theta t will behave, will converge in distribution in some sense to pi indexed by theta star. Same thing for the kernel. Maybe the kernel indexed by theta t, when t is large, will behave like the kernel p indexed by theta star. So, roughly speaking, the intuition is that at the end, we should obtain an estimate which is computed with point sample like that, but this estimate should have the same asymptotic behavior as if we were able to sample exactly the point xt under pi indexed by theta star, and to replace this estimate theta t by the value theta star. And it is exactly what we were able to prove in different schemes for the update for the stochastic approximation rule, the different scheme here for the value of h, but we were able to prove rigorously this intuition and show that this Wang-Landau algorithm can be used to approximate sample from pi. So here just I show you that it works. I show you. I don't. Does it work here? We apply this is our initial problem, the target distribution in 2 dimensions. We choose the strata as a partition of the x-axis. Here what I show you is the convergence of the theta t as a function of the number of iterations. There are about, I don't remember, 20 or 30 strata. Capital I here is, let us say, 30. And here you have the evolution of the 30 component of theta t. And you, graphically, you can understand that it seems to converge, to a value which is defined as theta star. And here you see the value of theta star as a which is the weight associated to each strata. You see that you have a large weight under pi of strata which have a mod in pi and a low weight at that level. It's quite logical, but here it's a way to observe theta star. Here I show you again the X component, the first component of the chain. And you see that at the beginning we decided to start it in the negative axis, and then it was able to jump on the positive one, and a larger jump up, go back to the negative side, and is able after that to move quite easily on both parts. And here I do not comment, it's just to show how I comment, is just to show how the exit time, if we start on the left side and we want to compute how long it is to be able to jump on the right side. Yes, we saw that this exit time is an increasing function of beta. Beta characterize, I didn't comment, but beta characterize the difficulty of is an inverse temperature parameter. The multimodality, when beta is large, it means that the target distribution is really highly multimodal. And so what you see logically is that the exit time is a bit more longer, but it's finite. And here the different curves depends on the number of strata. If you have many strata, the time to learn the value of theta star is a bit longer, and so the exit time is a bit longer too. So in this example, the conclusion of this first example is that we have a sampler. This sampler, each step of the sampler combines two things: a sampling step and an update mechanism of some design parameter theta t, which in our case is a vector of weight. In this example, the point xt have a special property. The conditional distribution of xt plus 1 given the past is given by this transition kernel indexed by theta t, designed to have its own invariant distribution. Each transition kernel has its own invariant distribution. And we also have in the background a way to learn to update the value of theta t following stochastic approximation scheme. Second example, we are on the other side now. We are in statistics. We have an optimization problem, and we will have to use at some point a sampling scheme. So let us discuss this application. A motivating example coming from pharmacokinetic. We suggest the following thing. We have n patients, and for each patient, so each patient at time 0 absorbs the oral administration of a drug. And then we observe the evolution of the concentration of the drug, just to understand the mechanism of absorption and the mechanism of elimination by the body. So there are many models to describe this mechanism that tell you that for the patient number I, if we observe the concentration in the blood, for example, at time 1, 2, 3 GI, then you have for patient number I many measurements, which tells you that the evolution of this concentration is a function of the time. So usually the model capital F, I do not give you the expression, but it's a nonlinear function of the time. So it's modeled as a Gaussian plus a nonlinear function of the time and some quantities. So usually the curves have this form. At time 0, you absorb the drug, the concentration increases, and then you have a decay. So this would be the perfect, I would say, the perfect curve, but in practice, there are some randomness due to the measurement, which are modeled by this epsilon. at time 1, time 2, and so on, T1, T2. And then also, there are some variability between patients, which is modeled here by the fact that each patient, this curve, this is roughly a curve, but for the other patients, the curve will be maybe more like that, or another one, it will be like that. No, not increasing, but already decaying. So there are some variabilities which may depend on the gender, which may depend on the age, which may depend on some genomic characteristic. And everything for the biologist is modeled by this random variable, xi, which governs the evolution of the curve, which they introduce classically a linear regression model. Here, Zi as a covariate, they are known, they are measured on each patient, but what I would like to learn through the measurement Y are the value here beta, the value of beta, in order to know which covariates are really important in the mechanism of absorption, and I would like also learn the covariance structure of the different noise introduced in the model. So if we want to answer to this question, and a possible approach is to use maximum likelihood techniques, which requires first to write the likelihood of the observation and then to be able to maximize this likelihood. And quite often, what happens is that they introduce here many covariates, but they know that only few of them are really important. And so they want also to introduce some sparsity constraint on the parameter beta. So it's not only a maximum likelihood, it's a maximum likelihood and their sparsity constraint on some part of the parameter, let us say at least on beta. In that model, if you want to write the likelihood, it is what we call a latent variable model, because writing the likelihood of Y is quite difficult. Here, it is a Gaussian, but here you have another random structure. And so what is easy is to say conditionally to X what is the distribution of Y, it is a Gaussian. And then, after that, you have easily the distribution of X, which is a Gaussian centered at the beta. So you are able to write easily the distribution of Y given X and the distribution of X. So you have the joint distribution of Y and X, and the distribution of Y is the marginal in X of the joint distribution. But the exact computation of the marginal here is not possible. So what you are able to write for this kind of model, and more generally what we call latent, what is called in the literature latent variable models, what we are able to write is an objective function, a likelihood, which is only defined through an integral. If we want to maximize the likelihood or its log or its logarithm, what you have to maximize is the logarithm of something you are not able to compute exactly, plus some sparsity constraint on some part of the parameter. So you have the penalty term, and you are faced with this optimization problem. You would like to minimize the negative log likelihood plus the sparsity constraint. But in this objective function, quite often this sparsity condition is explicitly, as an explicit expression, typically it could be the L1 norm of the coefficient beta, so you are able to evaluate this function. Usually it is a convex function, non-smooth function, not differentiable function. But this part here, the log likelihood in this model, is not explicit. So, what kind of tools to solve this optimization problem? Let us think first to strategies using gradient. Even if I said that some part is not smooth, but let us say we would like to use a gradient approach. There is a part of the objective function, the log likelihood, which is not explicit, but it doesn't matter. We are interested in this gradient. So what happens in the gradient of this part? Assuming that everything is regular enough in order that you can do a permutation of the gradient and of the integral. So the log likelihood, remember that the log likelihood of the observation for the of the parameter theta associated to the observation is defined as an integral of a joint distribution. I write it like that. Integral with respect to the distribution of the missing variable, dx. So if you want to compute the derivation with respect to theta, you compute the derivation with respect to theta of the integral divided by the integral, because you compute the derivation of the log. Here I said that we can consider that the model is regular enough so that you can permutate the two things. So here you say that it is the derivative of pi of p divided by the integral. You introduce the same quantity here, and what you have here is the derivative of the log multiplied by something which is a distribution. A distribution, and in statistics it has a name, because this quantity in statistics is seen as a joint distribution, and here you have the marginal with respect to the x variable, which means that this quantity is known as the a posteriori distribution of the observation of the missing data, of the missing data x given the observation. So your gradient has a special expression, a particular expression. It is a derivative of the log of the joint distribution. And since the missing data are missing, the data x are missing, it is the mean value of this quantity when the mean value over the a posteriori distribution of the x given y. Is it available? Is it a tractable quantity? The answer is no, for at least two reasons, at least two reasons. The first one is that quite often this integral is quite complex and it's not explicit. And the second one is that this quantity is not known exactly. It is known up to a normalizing constant. Here you have the likelihood, and the likelihood is not explicit. So the a posteriori distribution, like in Bayesian statistics, the a posteriori distribution is known up to the normalizing constant. So it doesn't matter. We know that we have a tool to approximate this kind of integral. We could use Monte Carlo techniques, sampling, for example, from MCMC sampler, which only requires the knowledge of the target up to a normalizing constant. So we have the numerical tools to approximate this gradient by a Monte Carlo sum. And on the penalty term, I told you the function g may be non-smooth, so which means that you cannot exactly apply a gradient technique. You have an objective which is a composite function, a part which is regular enough to speak about a gradient, another part which is not regular enough to speak about the gradient. So in my talk, tomorrow afternoon, I will tell you, I will give you what we can do in that case for the optimization of composite function. If you are familiar with latent variable models, you know that in statistics, the gradient approach maybe is not the most popular one. Quite often, I don't know if you know the expectation maximization algorithm. Some of you? Yes? Some of you. So the expectation maximization algorithm, the idea is not a gradient approach, it's more what we call a majorize minimize algorithm, a MM algorithm. At each iteration, we compute an auxiliary function. So let us say that we want to minimize a function which is like that. You would like to find the point here. So we have a current value theta t. At theta t, we define, at this point, we define an auxiliary function which is equal to the function of interest at the current point, like in Newton algorithm. And then you will, this auxiliary function has some nice property in such a way that if you define the next point as the minimum of this auxiliary function, you improve the value, which means that there is a decay of the objective function here, this one. This is the objective function. And the new point f evaluated at the new point is lower than f evaluated at the previous point. So you have a descent mechanism, and hopefully you should converge to theta star. In this case, we could try to apply the EM algorithm, except that when you define the EM algorithm EM for expectation maximization, which means that it is an iterative algorithm, and each iteration is divided into two steps, an expectation step and a minimization step, or maximization. Here I wrote it in the mean form, but here the expectation step is nothing more than defining this auxiliary function. And you see that the definition of this auxiliary function requires, again, the computation of not the derivative this time, but the log likelihood, the complete likelihood, the log complete likelihood under the a posteriori distribution. And here again, you are not able to exactly compute this function. You will only be able to compute the Monte Carlo approximation of this function. And you lose all the property of the EM, which means that if you decide to define the next point as the minimum of this criterion where the exact function is replaced with an approximation, Q hat, you can run these techniques. Why not? You have to study it. There is this result in the literature that show you that it may work, but you lose the nice property, the descent property. You cannot be sure anymore than the next point defined as the minimum, if it exists, let us say a local minimizer of this auxiliary function. You cannot be sure that you will have a strict decay of the objective function along the iterations. So in both approaches, gradient-based or EM approaches, we are faced with the same difficulties. We are faced with the difficulties, which is to say that we have to compute an integral with respect to the a posteriori distribution, an integral which is intractable, but the idea is to replace this integral by an approximation. So we could use quadrature techniques, but the behavior is quite poor when the dimension of the state space is large. We could use ID sampling to approximate the integral by a Monte Carlo sum, but ID sampling is quite unrealistic in our case due to the difficulties on this target distribution. And so we will have to use a third solution, that is, at each iteration, we will design a MC-MC sampler targeting pi index by the current value theta t. So this point depends on the time, and we run the chain for, let us say, m points, and we will use these m points to approximate the integral. And does it work? Yes, we have many papers on that kind of EM and gradient-based algorithm for the computation of penalized maximum likelihood in latent variable model. And here it's again to show you that we can observe convergence of the parameter and convergence to the minima under the assumption that the objective function is convex, otherwise to stationary points in some sense. So the conclusion is exactly the same as for the previous example, except that it is in the other sense, meaning that we want to solve an optimization problem, and in the background we will have a sampling mechanism that we will feed our optimization techniques in order to be able to compute intractable quantities. So always the same scheme, either the sampling or the update of the unknown parameter. This will be our scheme for all my talks. And the question now is, I will only address this one. If we want to if we have this mechanism that we update, we sample point xt plus 1 given the path by using a transition kernel indexed by theta t, we have to derive a theory to study the distribution of the point xt. Let us consider the simple case when all the transition kernel have the same invariant distribution. all the transition kernels have the same invariant distribution. You have a family of transition kernels. They all have the same invariant distribution. And at each iteration, you pick one of them with some random mechanism, not uniform one, a mechanism θ which may depend on the past samples and which depends on the past sample in our case. You pick at random, with this random mechanism, one of the kernel to obtain the next point, and so on. Do you think that at the end, the target distribution will be pi, if pi is the common of all the kernels, if they all have the same invariant distribution? The answer is no. No, you may lose the invariant distribution. They all have the same, but you may lose it. And I just comment this small example. Just to be convinced, you have a chain taking two possible values, 0 and 1. You have two, in your family, you only have two kernels. The first one is given by this transition mechanism. The second one is given by this one. You start from xt, let us say xt equals 0. Xt equals 0, you decide to sample the next point by using the kernel indexed by 0. You obtain 0 or 1. If the next value is 0, you again use this kernel. If the next value is 1, you use this kernel. So it's quite simple to write what is the transition matrix of this. When you start from 0, you will use the matrix P0. When you start from 1, you will use the matrix P1. The invariant distribution of this matrix is a uniform distribution, 1/2, 1/2. This one also. But the invariant distribution of your adapted mechanism here is not the uniform distribution. It is proportional to T1, T0. Which means that the fact that you adapt the sampling mechanism at each iteration may totally destroy the convergence, totally destroy the property, the ergodicity of the chain. So we need some theory to study this kind of phenomenon of mechanism, and this will be my talk this afternoon. Thank you.